Good day and welcome to part one of our discussion on Lagrange multipliers. So Lagrange multipliers is going to continue on our discussion from the previous section, and it is a specific method for optimizing functions. That is finding absolute maximums and minimums, but it's going to be relative to a constraint. That is, we want to maximize or minimize a function of multiple variables, so this could be a function of two variables, or as we will see, even more, relative to some constraint. And that constraint we will typically think of as another function, but equal to a value. So kind of the maybe simple way to think about this would be, what is the maximum volume of a box relative to a constraint, like a certain fixed amount of material to construct the box? Or more from an economic perspective, what is the maximum profit that can be achieved when you have some fixed cost that you are dealing with? And the nice thing about this approach of Lagrange multipliers is that the idea of how it works is very geometric, and I'm going to represent it with a picture. We want to maximize or minimize a function, f, relative to this equation g of xy equals k. And as a reminder from our previous discussions, when you see g of xy equals k, this is really a level curve. So what we need to do for the function f is find the largest level curve of f that intersects g equals k. So if we think of some level curves, i.e. if we have a contour map, there's going to be a whole bunch of these contours, and I'm going to kind of randomly draw them in here. So this maybe say f of xy equals 5, and then another contour which we draw in, say f of xy equals 7, and then another one, f of xy equals 9. And what we are trying to determine would be, and this is for maximizing, what is the largest level curve that intersects the surface? And we've drawn this somewhat intentionally so that we can see precisely the point where the largest, in this case the 7 level curve, intersects g of xy equals k. And the observation I want to make is precisely at this point. If you were to look at that point, it lies on the f equals 7 level curve, which means the gradient of f at that specific point is perpendicular to the blue level curve. And furthermore, note that this point that we determined also lies on the red level curve, which means the gradient vector to the g function would be perpendicular to the red level curve at that point. And note, the only way this happens is when the gradients at this point are scalar multiples of each other. That is, they point in the same direction or they point in opposite directions. So the big, really important observation to make is that the largest level curve of f intersects this constraint g of xy equals k precisely when the gradient of f is a constant multiple of the gradient of g. So we're thinking the lambda is a scalar quantity. And this is the key idea behind the method of Lagrange multipliers. So the method of Lagrange multipliers, I'm going to go ahead and state it here in words, and then we'll look at a very nice concrete example that illustrates the idea. To find the maximum and minimum values of a function of, in this case I'll say 3 variables, but it works just as fine with 2 variables as well, subject to some constraint. And remember, that might be maximize or minimize the volume of a box relative to how much surface area we can use. And there's some kind of assumptions here we won't worry about, but to procedurally use the method of Lagrange multipliers, we kind of follow a 2-step process with really the work taking place in this first step. We find all values x, y, z, and lambda with this equation satisfied. And I do want to make a small note here. When we say find all of these values, we're thinking a point of the form x comma y comma z are the points or the locations of the potential absolute maximums and minimums. And we find those to be the points that satisfy where the gradient of f is lambda times the gradient of g, along with the constraint equation being satisfied. Once we can find this list of points, we evaluate f at each and every one of the points. That gives us a list of values. The largest would correspond to the absolute maximum. The smallest would correspond to the absolute minimum. And I want to note that this actually does turn out to be something we can work with. It will in fact give us 4 equations and 4 unknowns. And just to make sure this is clear, let's just note what they are. The unknowns are these quantities x, y, z, and lambda, whereas the 4 equations are coming from 3 in the gradient and 1 in the constraint. So in the gradient, we would have the partial f sub x is lambda g sub x, the first components. The partial f sub y is lambda g sub y, the second components. The partial f sub z is lambda g sub z, the third components. And then lastly, we have this constraint, g of x, y, z equals k. So 4 equations and 4 unknowns. Let's now go ahead and investigate this in a nice concrete example that will allow us to visualize the scenario. So we begin with a very standard example of Lagrange multipliers. We have a function of 2 variables. F of xy is x squared plus 2y squared, which we would like to maximize and minimize on this constraint given by x squared plus y squared equals 1. So that our constraint function that we get, we have g of xy equals 1, but it's really x squared plus y squared is our function g. So let's consider what this will look like graphically. So to the left, we now see a graph of our surface given by the function x squared plus 2y squared, a paraboloid opening upward with a vertex sitting at the origin. And what we would like to know is if we restrict our inputs to lie on this circle x squared plus y squared equals 1, how big can our outputs be, or how small can our outputs be? So if I think about what that would look like on our surface, you would end up getting a graph that looks something like this, where it kind of dips down and it has those lower values corresponding to what looks like it's above the x-axis, and these higher values that look like they correspond to being above the y-axis. So this is kind of my rough picture, but let's go ahead and use Lagrange multipliers, and then we'll look at a much better graph that comes from GeoGebra. And if you want to see that graph from GeoGebra before you get started with the computations, fast forward to the end of the video and then come back for the computations afterwards. Okay, so applying the method of Lagrange multipliers, and note this is a key problem for Lagrange multipliers. You have a function you want to maximize or minimize relative to some constraint. So Lagrange multipliers tells us that the gradient of f is lambda times the gradient of g, and we have this constraint equation x squared plus y squared equals 1. And this should really break down into 3 separate equations. We have 2 equations coming from the gradient along with this constraint. And remember those equations that we have coming from the gradient, and I'm going to write out a few steps. We would have fx, fy, the partials, is lambda gx, gy. So that f sub x is lambda g sub x, and f sub y is lambda g sub y. And then we have the constraint equation x squared plus y squared equals 1, which will give us 3 equations and 3 unknowns. And in future problems, I'll probably just jump immediately to these equations, but it's worth seeing a few of these generic computations to make sure we understand where these partials come from. So looking at our functions of interest, we have f is x squared plus 2y squared. So that our equations will essentially become, and I'm going to line them up way down here to the left, we have f sub x, 2x, is equal to lambda g sub x, 2x. F sub y, 4y, is equal to lambda g sub y, 2y. And then we have x squared plus y squared equals 1. And what we would like to do is solve for the values of x and y that satisfy these three equations. And there are many different techniques, and this is really the difficulty. It's typically not an easy thing to solve this system of what we'd call nonlinear equations. But overall, I would say the standard idea is you work with the equations coming from the gradients until you have enough information to use that constraint equation. So using the constraint is the last step in our work. That's very important. Using the constraint is the last step. So if we focus in on these gradient equations, one technique, or in this case observation we can make, is if we look at that first equation, 2x equals lambda 2x. There's two possible ways that equation can be satisfied. You can have lambda is equal to 1, or you can have x is equal to 0. And those are the only two possibilities. So let's start with lambda equals 1. For lambda equals 1, we have to go to our second gradient equation to see what we can get. So if lambda is equal to 1, that second gradient equation will give us 4y equals 2y. So 2y equals 0, which means y equals 0. And once you get it down to this point, now you can use the constraint equation. If you substitute y equals 0 into that constraint equation, what we will have is x squared plus 0 squared is 1. So x squared is 1, which means x is equal to plus or minus 1. And that gives us two possible points, when x is 1 or when x is minus 1. But in either case, they came from setting y equal to 0. And note, this is really just our first possibility, but follow kind of our reasoning. We worked with the first equation to get lambda equals 1. We used that next gradient equation to boil down to y equals 0, which allows us to substitute into the constraint. And the entire goal is to get to this point where you can substitute into the constraint, which is essentially the last step. But we have to repeat this. The same thing for x equals 0. Now note, when x is equal to 0, we're already at this point where we can substitute into the constraint. So that's actually the ideal scenario. So x squared plus y squared equals 1, but x is 0. So y is equal to plus or minus 1. And that gives us two more potential points. When x is 0, y is 1, or when x is 0, y is minus 1. And for these 4 points that we've determined, we need to know what are the function values at those points. So f of 1 comma 0 and f of minus 1 comma 0, looking up at our function, both give us an output of 1. F of 0, 1 and f of 0 minus 1, the function output at both of those values give us 2. So the first two where we have 1 corresponds to an absolute minimum, which would correspond to 2 points we see on our curve to the left. And at the points 0, 1 and 0 minus 1, so along the y-axis on that circle x squared plus y squared equals 1, we have our absolute maximum values. And graphically we can see those values as well. So to finish up, because I know the work always seems really abstract, at least in the beginning, let me show you a hopefully much more clear GeoGebra image, which we can now see. In orange, we have the surface corresponding to the graph of x squared plus 2y squared, this paraboloid we indicated previously opening upward. And what I'd like to do is kind of just hit play on this and follow along. So we want to know how big or how small will this be relative to x squared plus y squared equals 1. So essentially that is, if we look at this cylinder, where does it intersect the surface? And putting in that equation for the intersection, this curve in black, we can now hopefully more clearly see kind of this almost Pringle chip feature that we had drawn in previously. And we would like to know along this black curve, that is, we're on the surface, we're corresponding to inputs of the form x squared plus y squared equals 1, how big and how small will the function be? And hopefully this gives you an illustration of what we saw, is that biggest value sits directly above this point corresponding to y is 1 or negative 1. And that smallest output sits directly above the point 1, 0 or minus 1, 0, which is the exact observation that we made. So hopefully that gives a bit more geometric intuition. In the upcoming videos, we will spend our time practicing just more and more examples of this method of Lagrange multipliers.